Up first this morning, we have Russ White. Russ.
Good morning, y'all. Welcome to the Deep South, where they serve ice with their tea. We wouldn't want you to have hot tea, we want you to have iced tea. It's very good, yes. I'm kind of used to this because I was born and raised in Atlanta, and you can now say, oh, I feel sorry for you, but that's okay. So, I'm going to be talking about trade-offs in network complexity. I think we'll cruise through this and you'll see what we're trying to get at here. They put me behind a podium. It's going to drive me crazy. I have fallen off stages before though, so it's probably good that there's actually a podium in front of me to keep me from doing that. So let's talk about network complexity. So how many of you guys know what network complexity is? Yeah, a little bit. Okay, so you can give me a definitive number for the complexity of your network, right? No. Okay, didn't think so. So let's talk through some stuff here. We're going to talk about defining complexity, how to measure some complexity. So, and we're going to talk about an interesting idea that is in a draft before the Network Complexity Working Group or Research Group in IRTF. Called the complexity trade-off. I think this is something we actually deal with on a daily basis. We're going to use fast reroute as an example. Given that I do a lot of work in fast reroute, I'm not saying fast reroute's a bad thing. I'm just saying this is an example of understanding complexity trade-offs, and then we'll talk about wither complexity a little bit. So what is network complexity? How do you measure this? What's interesting is there's been an awful lot of work in this area recently. There is this thing called the Network Complexity Index. You may have seen this. This is actually based on work in social media networks rather than on computer networks, but they're very similar in many ways. And there's a very simple little formula there where you have b to the n equals max j, x to the j greater than or equal to I. And then you can see the actual way to use that formula there. So I expect you to run right home and use that on your networks. Essentially, this formula or this index tries to calculate or figure out the interaction between communities within a network. So imagine you have a great big pool table, the world's largest pool table, and you have all these pool balls wandering around quasi-randomly through some magical force. So what Network Complexity Index does is it says, I can place a grid over this pool table and I can kind of figure out where the communities lie and I can figure out the interaction between the communities or the grid markers, and that allows me to figure out what the complexity of the network is. So you might look at this in a computer network as control plane state, BGP updates, OSPF updates, ISIS updates, and then there's that protocol people put on their gravestones. What was that? Oh, RIP, sorry, RIP, yes. So it really is based on the number of nodes, the degree of the nodes, the amount of connectivity, the number of edges, and the rate of change of nodes and edges and their connectivity. So that's what the Network Complexity Index is. This is kind of a cool measure, but we'll see in just a minute what it doesn't measure. There's another one called NetComplex that was, you can see the URL down there at the bottom of the slide. I assume you can read it because I can't from up here. But anyway, you can see that there's this thing called NetComplex, and there's a bigger formula there, and their metric is to try to compute complexity from state and function. So whereas Network Complexity Index actually tries to break the network up into communities, the NetComplex actually tries to treat the control plane as one big thing, and it tries to compute a single complexity number by summing all of the nodes and edges against each other and the rate of change and stuff. This kind of pits distributed against centralized algorithms a bit. I think centralized algorithms tend to work better in the NetComplex number, and it does try to make note of aggregation and some other mechanisms to hide information and reduce control plane state. Then there's this draft that's in Network Complexity Research Group in the IRTF that talks about design intent. And what they're trying to do is they're trying to take a configuration of a device and break it down into independent components and then figure out the relationship or the network of connectivity between the different configuration components in the device itself. So this is pretty interesting because they're working at the problem from a different direction. They're working at the problem from objects, references, and a referential link. So this is fairly interesting concept that they're working with here. Okay, what's the problem with all these? These are some pretty good tools for figuring out some network complexity numbers. But there's a couple of problems with these. First of all, they focus on a very small part or small slice of what I would consider overall network complexity. Each one of these tools tries to provide an absolute measure in the one specific area that it's dealing with. For instance, control plane state, the rate of change. Can you measure these things and figure them out? The problem we have is that systemic complexity isn't an absolute number like this. I cannot look at my control plane state and figure out what the overall complexity of my network is. Why? Because my control plane state includes things like aggregation, information hiding through layering of topologies, virtual overlays actually are information hiding techniques. So how am I actually interrelating these different control plane sets and different control plane states to an overall complexity number? So these are good tools, but they only cover a particular small slice. A second problem we face is that if we go back to my big pool table, and I have all of these balls rolling around semi-randomly, networks aren't built that way, right? There are some aspects of network design that are quasi-random. For instance, traffic flows can be quasi-random. They can often be put on a Bayesian or on some sort of a fractal measurement or formula. You can figure out some things about traffic flow. But in general, networks are organized. I mean, we're all network designers and architects, right? What we do is we design networks to solve certain problems. So there's an intention issue here. So if I take that same pool table and I put all the balls in a single line, nice and ordered, rolling in the same direction through some magical process, all of a sudden, all my network complexity or all my complexity formulas go out the window because I've added organization or intent to the entire process. So where we are. Statistics will be of limited use in this realm. There's this actually great quote here from a guy writing, Dr. Weaver writing in 1948 on this entire topic. He says, this is at the very beginning of the statistical analysis phase of big data, you might call it, when they were first doing some of this type of stuff we're doing in big data to do statistical analysis today. He said, they are, and he's talking about biological processes and some other things that deal with complexity, problems which involve with dealing simultaneously with a sizable number of factors which are interrelated into an organic whole. They're systemic, so they actually interoperate with each other. They are all, in the language here proposed, problems of organized complexity. So in 1948, Dr. Weaver was making the point that we have very good, at that point they had made very good strides in disorganized complexity. We've actually made a lot more strides in disorganized complexity to this point, somewhat 70 years later, but 65 years later, whatever it is. But in the case of organized complexity, we still haven't done a very good job of dealing with organized complexity. So somehow or another, we have to learn to deal with intent. So now let's look at the way I think we have to deal with intent. And that is through complexity trade-offs, right? Eric Osborne, who's a friend of mine, always says, you know, complexity is what you don't understand, right? So the first thing we have to realize about complexity is here to solve a problem. When I do a network overlay, I'm adding complexity to my network. If I use an MPLS L3 VPN or a VXLAN or some other tunneling mechanism, okay, you can all yell at me now because you don't think MPLS is tunneling, but that's okay. Anyway, some other tunneling mechanism to get through solving a specific set of problems, I've added complexity to my network, I've added another control plane, but I've done it to solve a specific problem. So complexity has no meaning outside the context of the problems being solved, right? Houses would be a lot simpler to build if everybody used nails for everything, but they don't. We use screws for a purpose. Screws are more complex than nails, but we use screws for a purpose. That's one of my favorite lines in the world, by the way, right there. How many balloons fit in a bag? So the other thing is complexity versus your tool set, right? More complex problems can be managed with better tools. All right. I know everybody sitting in this room probably has Perl scripts or Python scripts that manage their configurations, right? Nobody here goes out and manually manages their configurations on their boxes. What we've done is we've actually taken a complex problem, managing a diverse set of configurations across a large number of devices, and we've reduced the apparent complexity by adding a tool to the problem. So again, if your only tool is a hammer, every problem looks like a nail. But what if you have a nail gun or a sonic screwdriver? Of course, nail guns are harder to maintain than hammers, and sonic screwdrivers are notorious for breaking, if anybody watches Doctor Who. But, nonetheless, they're effective tools. So there's a trade-off here as well. There's the complexity versus the skill set. I don't know about you, but when I was in Cisco TAC, all my TAC engineer friends looked like the guy in the middle most of the time. But this is your knock. Some of your guys are really curious and don't know what they're doing. Some of your guys are dead tired, and some of your guys are really intelligent but a little bit bashful. It's a great illustration. But this isn't just a matter of intelligence, it's a matter of focus and training. You've got to have the right skill set to apply to the right problem. So the better your skill set is, the better your ability to handle complexity of various types. Another thing we often don't realize is that complexity comes in pairs. This is an RFC 1925, a couple of quotes from RFC 1925, one of my favorite RFCs. It's easier to move a problem around by moving the problem to a different part of the overall network architecture than it is to solve it. And it's always possible to add another layer of indirection. So quite often, we decrease complexity in one part of the system, but we end up increasing complexity in another part of the system. So I have this cute little complexity graph, but I'll give you one example here. Here, I have, or even here, in any of these slides in these trade-offs, I have a set of tools, right, that I am using. I have added complexity to my life by buying a sonic screwdriver. There is no doubt about it. I'm using the sonic screwdriver to solve a set of problems that are almost impossible to solve without the sonic screwdriver, however. So I've reduced the apparent complexity in my network by adding Python scripts or Perl scripts or some sort of network management program to handle all my configurations. But now guess what? Somebody's got to manage the scripts. And somebody's got to manage the application. So yes, I've reduced my apparent complexity, but I've added complexity back somewhere else. So the point of this slide is that complexity has a counter complexity. When I add a tool or I add something to reduce my complexity, I'm actually increasing complexity somewhere else. I need to be aware of this and think about it. I can't just throw complexity over the fence to the network management guys. You just can't do it. You can do it, but it won't work but so long, and then that piece of the part will fail. So then partially also, my third line here is my function line. I have a particular set of services I'm trying to offer. As I increase the amount of services I'm trying to offer, clearly my complexity level has to go up. So there's a sweet spot between complexity, counter complexity, and function that I've got to get to. Anybody ever watched the movie The Point? No? As the rock man says, you don't have to have a point to have a point. But anyway. You can never reach some desirable goal without adding complexity. Decreasing complexity in one point will nearly always increase complexity somewhere else. Increasing service levels or solving hard problems is always going to increase complexity. So some bad questions. How complex is this? My favorite, will this scale? My answer to will this scale is always, how many balloons fit in a bag? I have no clue. Let's think about all the possible situations and think about it. Okay, good questions. Where will adding this new thing, overlay, protocol, control plane, tool, piece of training, increase complexity? If I reduce complexity here, where do I increase complexity? And if I reduce complexity here, where will suboptimal behavior show up? Okay, I'm gonna paraphrase Yakov for a minute. You can bring your traffic to the service, or you can bring your service to the traffic. Right? Pretty much. So I love network virtualization, network function virtualization. It's a cool idea, but what are you doing? You're bringing your packets to the service. Which does what? Which increases stretch in your network, which means you're actually using more bandwidth to get stuff between services. So what you're actually doing when you look at service chaining and all these other solutions, again, I'm not saying they're bad solutions. I'm just being realistic about what you're doing, is you're increasing stretch, increasing bandwidth, increasing jitter, increasing latency in order to reduce the number of places you inject policy in your network. It's pretty straightforward. It's not necessarily a bad trade-off, but it's a trade-off we've got to be conscious of. So complexity at the systemic level is about trade-offs, not absolutes. So here's fast reroute as an example. If anybody's interested in other examples, there are other examples in the slide set after the end slide that you can look at that I've worked through some other ideas. So just to give you, this is just one example. All right, fast reroute. I've been working in fast reroute for an awful long time. Think about how we went through in routing. What was the maximum convergence time of an IGRP network? Not EIGRP, IGRP. 9 minutes. RIP. 180 seconds to 3 minutes. OSPF. If you count all your timers out, your maximum is in the 3-minute to 2-minute range. So what did we do? We tried to make it route faster. So what do? First thing is we do LFAs, and we do a pre-compute. We know in this case that A has a best path through B to E, but we know that it has an alternate path. We can see it on the network diagram. The routing protocol can't see it because of the way the metrics work, right? This is effectively the feasibility condition in EIGRP. If my backup path or my alternate path is more than the cost of my best path, I cannot trust the path not to be a loop from a routing perspective. So LFAs are essentially the same thing. I'm just looking at my metrics and I'm just saying, hey, this might be a loop, I can't use it. Or it will create a micro loop if I use this. So in this case, I do a pre-computation and I actually discover that A can use C as its next path, even though it's not the best path. I actually pre-compute out that it's actually not a loop using some clever math and make it work. So here's what's called a loop-free alternate. A can compute the cost of C to determine if traffic forwarded to the destination, in this case 192.02/24, will in fact be looped back to A if it's sent to C. If not, then A can install the path through C as a backup path. I get a lot of faster convergence. What's my cost? See, the point is, there's a complexity trade-off here. What's my complexity trade-off? I get faster convergence, I get better optimality in my network. What's my trade-off? I have an additional computation a day. I have to run SPF a different way or have to run it multiple times. Frankly, this is almost nil. Second thing, though, from a network designer's perspective, is I now have to think about C as an alternate path, which means quality of service, it means bandwidth, it means jitter, it means delay, it means thinking through, if I want A to have an alternate path, where I'm going to put that alternate path and how it's going to work. So now let's go one step further. Let's do tunneled LFAs. If I tunnel into Q, I have P space and Q space, and essentially I'm trying to get to a point in the network where A can safely tunnel traffic and have it actually dump towards the destination rather than looping back to A. If C is not there, I can go past C. I can compute and go past C and say D is where I can dump my traffic. Great. So I can dynamically build a tunnel through C. So I skip C because if I send the traffic to C in this case, it'll loop back to A. So I skip C, I tunnel around C, I get to D. I know D won't loop the traffic back to me. There's a lot of ways of doing this, right? There's not via, there's MRT, there's remote LFA. There's a lot of different ways you can do this. There are different computation mechanisms. MRT is different than not via, which is different than remote LFA. And there's different tunneling mechanisms. Almost everybody's down to MPLS as the tunneling, but there's absolutely no reason you couldn't use GRE or something else in this situation to tunnel past C. What are my gains? I have relaxed network design rules. Before, when I looked at my network design, a ring meant I was either going to have a micro loop in my convergence, or I was going to have some sort of slower convergence. I can eliminate my micro loops. I can do faster convergence. What's my cost? I have additional computation today. Again, almost nil. SPF costs me nothing to run in the real world. But now I have to have a dynamic tunnel. All right. Now I have dynamic tunnels. Can somebody dump into a dynamic tunnel to bypass a firewall rule someplace on me? To bypass a policy? What implication does having dynamic tunnels in my network, dynamic tunnel destination points in my network, have on my security posture and my policy implementation? What do I do with that? Now I have to also, again, design network with alternate paths in mind. I go back to my QoS. I have to go through all this other stuff, right? So basically, the point is that there is a trade-off here, and we need to think about that trade-off as network designers and architects, and not just assume that I'm getting and I'm not giving anything. Okay, with or complexity. Where do we go with all this stuff? Will we ever have a single number that tells us how complex a network is? My opinion is no, because networks are systemic and they're intentional. Design is intentional. I don't yet know how to measure intent. There may be somebody out there who can figure out how to measure intent and relate it to a set of configurations and policies and say, oh, you intended your network to solve this problem, and therefore I can give you a complexity number for the minimum complexity that will be able to solve that problem. But then, how many of your networks only solve one problem? Yeah, I didn't think so. Nobody's network solves one problem. Everybody's network in the world solves multiple problems. So now you've got to interact intent, which then becomes a matter of business policy. And I've got to start thinking about which intent is more important than the other intent and stack ranking things and figuring that out. I do, however, think that we'll have a bunch of numbers before this is over with that'll help us characterize specific parts, like what is my control plane state if I do this? What happens if I get a link flap over here to my network complexity? How does that all work? If I push policy here, what happens to my management complexity versus my stretch in my network versus my optimality of actually using the network in the best way possible? Will we ever have something that you can point to that says, this is complex or that won't scale? I don't think so. I think that is always going to be the realm of network engineers who've flown by the seat of their pants long enough to know that when you make that turn, you're turning too sharp. And I think that's the way it's always going to be. Again, we can use the complexity numbers we can come up with to give us some ideas, but we're not necessarily, or put some definition around elegance, but not necessarily to actually get to the point where I can point to a number and say that is too complex or that won't scale. Now, I'll tell you one thing is, one useful result, I don't know if anybody else has noticed, but when I first got into networking, I was installing VT100 terminal cards in Z100s at McGuire Air Force Base. And we thought it was really brilliant to store all of our data in the mainframe. So there's one set of policies around the data and one control point and one set of user accounts and how beautiful that was and everything. And then people started installing Z225s and Z250s in their back closets and putting Lotus 123 on them to do the financial stuff and blew our entire data model apart. So we thought we'd be really brilliant and try to re-centralize with SQL and middleware. Everybody knows how that worked out, right? So my point is that we're playing this pendulum, okay? Every 2 or 3 years or every 5 years we say, oh look, centralization, it's a shiny thing. And we're like Dory and we run off after the shiny thing. And then we say, oh, look, decentralization, it's a shiny thing. And then we go under or we go through the cloud of jellyfish instead of trying to go over them, right? Part of the point here is that if we can start characterizing complexity and really understanding where the trade-offs and put some numbers around the trade-offs where we can and learn to recognize it for what it is, we can stop this back and forth complexity or centralization, decentralization game and try to right-size the data and right-size the network where it needs to be. So theoretically, part of my game in trying to get involved in the network complexity research group is that my experience in the networking industry is we need to reduce the frequency and the amplitude of this pendulum swing that we're on, and because we're just driving ourselves crazy with it. Same slide. So one way forward, measurements within a framework, try to build a framework, try to understand and lay out all the trade-offs we can think of. document the trade-offs we find in real life so that the researchers who are working in these areas, the real researchers that are doing the mathematical work, can understand better how to or what they should be focusing on, what the slices look like, and what these slices should do, and where they fit into the big pie. And we're the network architects and engineers and designers. The math guys are really good at math, but I wouldn't trust some of these guys to design my network. So you've got to think through what we can bring to the table as architects and engineers is to actually lay out what these frameworks should be to do this work within. Second of all, it also could help build a body of knowledge. So how many new network engineers do you know walk in and they ignore the power of unintended consequences, right? They go out and, install a static route to make something work and create a loop that shuts down the mainframe or the cloud for a day or two while you're trying to get your change control people to do an emergency meeting. And so, or, add that 9th switch or that 20th switch onto that spanning tree and make the whole thing collapse. So, this building a body of knowledge where we can actually start training people and teaching people to be better designers and teach each other to be better designers through understanding the trade-offs that we've seen in our own work, I think would be really useful. There are a lot of efforts to measure and describe this stuff. I've mentioned the Network Complexity Working Group. Actually, it's a research group. I heard on the slide there wrong. It's an IRTF working group. It's really good. There's some really good meeting materials and some really good drafts out there in this area that you should read. The math can be a little bit weird sometimes. So, part of maybe what we could do as network engineers is to try to get the mathematicians to explain themselves in terms that we can actually understand better without having to do the integral functions and everything like that. So anyway, there's one particular draft. This presentation parallels a draft that Alvaro Botana and I have been working on, which is right there on the screen, Design Complexity Trade-Offs. And that's within the NCRG. So basically, bottom line, think about the trade-offs. If you can get involved in the NCRG and help us define this stuff, it's very useful. Start thinking about it in your own work, the trade-offs, and start thinking through some of the material that's out there in the network complexity field. And that is the end. Like I said, there are a bunch of other slides on this that are probably posted if you want to go through some of the other examples. So that's it. Any questions? We have 1 minute and 54, 53, 52, 50, 50. Tony.
Thanks, Russ. Tony Tauber, Comcast. So, I guess you get left with the so what of all that. How do you, if you're always squeezing the balloon in one place and then squeezing it in another place,
it always comes out in the
how
other.
do you decide? And then, how do you characterize it to your management, your financial people, and
Right.
then are you always, what's the complexity that's outside the network, for more staff, more skills, more money, more spare parts deployed all over the place? Or
Yeah. So I think unfortunately we're at the nose end of this camel. And I don't think we know enough right now to actually to have any real result other than let's go look at this and figure it out and think about it. That's kind of my impression. Do you think that's accurate, or do you think there should be?
Well, I guess ways to characterize it and force people to think about it, and part of their design discipline is, I think, all to the good.
Yeah. You're out. We have one more. We have 33 seconds. Run into the microphone. How many times do you get to ask hard questions that I can't answer in your life?
All right. Thank you very much,
Okay.
Ross.
Thanks, guys.